Compressed air. At the completion of this course, you'll be able to identify the supply and demand sides of a compressed air system, estimate the annual operating cost of an air compressor, summarize the effect of losses due to filter pressure drops. We will briefly look at the supply side of the system. The supply side includes all the components prior to and including the primary receiver and the pressure flow controller, if present. Those components include one or more air compressors and various aftercoolers, traps, drains, filters, and dryers for achieving the required quality of air. The demand side includes components after the primary receiver and the pressure flow controller, including the distribution and storage components and end-use equipment. A properly managed supply side results in clean, dry, stable air being delivered at the appropriate pressure in a cost-effective manner. A properly sized transmission system economically minimises pressure loss due to the flow of compressed air out to end users. A properly managed demand side minimises wasted air and uses compressed air for appropriate applications. Achieving and maintaining peak compressed air system performance requires addressing the supply components, transmission system, and demand sides and how they interact. The air distribution system on the demand side is intended to deliver air to the point of use with minimal pressure loss. It is often an extended network of main lines, branch lines, valves, and air hoses. The length of the network should be kept to a minimum to reduce pressure drop. Piping should slope to allow for drainage of condensate and include traps for its removal. A typical compressed air system includes distribution piping serving different departments or buildings. Small but critical loads needing special drying or filtration can be served efficiently off the main loop. An example is the instrument air system. This saves the added expense to dry and filter the whole plant air system for this small load. Many plants contain applications with intermittent demands for high volumes of air. This can cause pressure fluctuations and may starve some points of use, which can adversely affect the quality of final products. A secondary receiver tank may be installed on the demand side to help manage demand peaks. If the high demand periods are fairly short, the secondary receiver can store enough air to meet that demand, and then it can be refilled without the need to add more compressor capacity. An inlet check valve will stop stored air from flowing back into the system and ensure that the boost of air is available when needed. When low pressure flow is required, consider using dedicated low pressure blowers. This saves electricity by using low pressure blowers instead of using expensive plant air. When significant high pressure flow is required, consider using dedicated high pressure compressors and dryers. This saves electricity by using small high pressure compressors instead of running the plant air system at a pressure higher than needed. Over the life of a compressed air system, energy accounts for 80% of the total cost of ownership, compared to just 9% for the initial cost of capital. Don't simply purchase the lowest cost equipment. Evaluate efficiency options to reduce costs and select system components for the lowest life cycle cost. There are many ways to ensure consistent, reliable, and efficient use of energy in compressed air systems. Reduction of demand. Because of the relatively expensive operating costs of compressed air systems, the minimum quantity of compressed air should be used for the shortest possible time, constantly monitored and comparing against alternatives. Maintenance. Inadequate maintenance can lower compression efficiency, increase air leakage or pressure variability, and lead to increased operating temperatures, poor moisture control, and excessive contamination. Better maintenance will reduce these problems and save energy. Monitoring. Maintenance can be supported by monitoring using proper instrumentation, including the following: pressure gauges on each receiver or main branch line, and differential gauges across dryers, filters, etc. Temperature gauges across the compressor and its cooling system to detect fouling and blockages. Flow meters to measure the quantity of air being used. Dew point temperature gauges to monitor the effectiveness of air dryers. Kilowatt-hour meters and hours run meters on the compressor drive. Reduction of leaks. Leaks cause an increase in compressor energy and maintenance costs. Quick connect fittings always leak and should always be avoided. In addition to increased energy consumption, leaks can make pneumatic systems or equipment less efficient and adversely affect production, shorten the life of equipment, lead to additional maintenance requirements, and increased unscheduled downtime. A simple way to detect large leaks is to apply soapy water to suspect areas. The best way is to use an ultrasonic acoustic detector, which can recognize the high-frequency hissing sounds associated with air leaks. Electronic condensate drain traps. Due to the necessity to remove condensate from the system, continuous bleeding achieved by forcing a receiver drain valve to open often becomes the normal operating practice, but is extremely wasteful and costly in terms of air leakage. Electronic condensate drain traps offer improved reliability and are very efficient as virtually no air is wasted when the condensate is rejected. Reduction of the inlet air temperature. Reducing the inlet air temperature reduces the energy used by the compressor. In many plants, it is possible to reduce this inlet air temperature by taking suction from outside the building. As a rule of thumb, each 3 degrees Celsius reduction will save 1% compressor energy use. Maximizing allowable pressure dew point at air intake. Choose a dryer that has the maximum allowable pressure dew point and best efficiency. A rule of thumb is that desiccant dryers consume 7 to 14% and refrigerated dryers consume 1 to 2% of the total energy of the compressor. Consider using a dryer with a floating dew point. Choosing the correct compressor for its load. Plant personnel have a tendency to purchase larger equipment than needed, driven by safety margins or anticipated additional future capacity. Given the fact that compressors consume more energy during part load operation, this is something that should be avoided. Consider a modular system with several smaller compressors to match individual needs, or a blower for low pressure requirements. Proper pipe sizing. Pipes must be sized correctly for optimal performance, or resized to fit the compressor system. Inadequate pipe sizing can cause pressure losses, increase leaks, and increase generating costs. Increasing the pipe diameter typically reduces the annual compressor energy consumption by 3%. Heat recovery. More than 85% of the electrical energy used by an industrial air compressor is converted into heat. In many cases, a heat recovery unit can recover 50 to 90% of the available thermal energy for space heating, industrial process heating, water heating, make-up air heating, boiler make-up water preheating, industrial drying, industrial cleaning processes, heat pumps, laundries, or preheating aspirated air for oil burners. Install variable speed drives. When there are strong variations in load and/or ambient temperatures, there will be large swings in compressor load and efficiency. In those cases, installing a VSD may result in attractive payback periods. To calculate the annual operating cost of a compressor, you need to collect the following data. First, you need the power at the compressor shaft. If the compressors are rated in horsepower, convert that value to kilowatts. You can multiply by 0.75 and round to the nearest 10 kilowatts. For example, if you have a 200 horsepower compressor, use 150 kilowatts. Note that most motors are designed with a service factor which allows them to be operated for short periods above the nameplate rated power. The service factor is often 1.15, so a motor producing 100 kilowatts can be operated up to 115 kilowatts. At full load, a compressor may operate at above the motor's nameplate rated power up to the service factor. Hence, at full load, the actual power is frequently higher than the motor nameplate, so check the equipment specifications rather than the nameplate. Next, you'll need the operating hours, which is the number of hours per year that the equipment is energized. You'll also need the unit cost per kilowatt hour of electricity. You may also need to determine the operating level and the percent time that the equipment is running at this operating level. If the equipment runs at the full load operating level for 25% of the time and at the semi-loaded operating level for 75% of the time, you will need to do this calculation twice, once for each load condition, and add the results. For each operating level, you will need to determine the percent of full load kilowatts used at that level. See published datasheets or use the manufacturer's part load specifications. Finally, you will need the motor efficiency at this operating level. The data collected is inserted into this formula, and the result is the annual operating cost of the compressor. Let's look at an example. Imagine an air compressor with these characteristics. It is running full time for 1 year. The power at the shaft is 200 kilowatts and the energy is 10 cents per kilowatt hour. Now let's look at its demand. 20% of the time it runs fully loaded, level A. 60% of the time it is at part load, level B, consuming 80% of full load power, and 20% of the time it is at part load, level C, consuming 60% of full load power. At each load level, there is a different motor efficiency. Here is our equation again, now with efficiency moved to the end at the right. Inserting the data into the previous slide gives us the first part of the cost of running the compressor. Here is our equation again, now with efficiency moved to the end at the right. Inserting the data into the previous slide gives us the first part of the cost of running the compressor. Insert the data for load level B and C into the equation and calculate the annual running costs at each level. Your answers should look like this. If you have an end use and know its flow, or you find a leak and estimate its flow, it's useful to put this into cost terms so everyone understands its economic value or loss. You can do this by determining the cost of 1 cmh, cubic metre per hour, per year. Then, for example, you can take the unit cost of air and multiply it by the leakage rate to determine the annual loss of leaks. First, determine the amount of air produced by the compressor. In this case, it is given as litres per second, which can be converted to cubic metres per hour. If it is fully loaded, the amount of air produced is the full load rating of the compressor. If it is partly loaded, it will be the reduced flow at that load. With this data, you can calculate the cost to produce 1 cmh per year, cubic metre per hour per year, by dividing the annual cost of operation of the compressor by the calculated rate of air production at the given loading. Part of the energy used to compress the air will be lost due to air filtration. We can estimate the energy lost using pressure drop across filters. To overcome the pressure drop, we can assume a typical compressor will consume 1 to 2% more power for each 140 millibar discharge pressure increase at normal pressures. In the compressor room, we typically see 140 to 200 millibar pressure drops, or more, for when filters are new. Therefore, we expect 1 to 2% compressor energy to serve filter pressure drop for new filters. Filters can be cost-effectively purchased and installed when the pressure drop increases by 400 to 550 millibar compared to the pressure drop when new. This loss will increase over time, so it is important to monitor pressure drop on differential pressure gauges installed across filters to help determine the optimum time to change them. As the differential pressure increases, the percent of power consumed by the compressor to service this pressure drop will go up. The cost of new filters can be compared to this additional power cost. The filters can be changed when the power settings justify the new filter costs within the required time period. This chart shows an approximate breakdown of cost for air production, drying and filtering on the supply side of a compressed air system when brand new and in steady, efficient operation. As the system deviates from design load or requires maintenance, the percentages will change and then the cost of compressed air increases dramatically. There are 4 categories of system demand: actual production needs, leaks, inappropriate uses, and artificial demand. Artificial demand is defined as excess volume of air consumed by unregulated end users as a result of supplying higher pressure than necessary for the point of use applications. Equipment fed through a pressure flow controller or through regulators will only use air at the regulated pressure. Equipment connected to part of the distribution system that does not have specific pressure or flow control will use air at whatever pressure prevails at the time. If the pressure is higher than required, all leak flows increase and all unregulated equipment will use more air than it really needs to do its job. This excess airflow is called artificial demand for compressed air. Unregulated use can be as high as 30 to 50% of air demand. There is a large financial penalty for higher than needed pressure. A rule of thumb for systems operating at around 7 bar is that increasing the pressure by 140 millibar will increase the energy consumption of the compressor by about 1% at full output flow. There is a second effect, that of the artificial demand, and that every air leak will also be worse at high pressure. That will increase energy consumption by another 0.6 to 1% because of the additional air being wasted. In a system where 30 to 50% of the use is unregulated, the combined effect can be a total increase in energy consumption of about 1.6 to 2% for every increase in discharge pressure by 0.14 bars for a system near 7 bar. Let's summarise what we have learnt today. The supply side includes all components prior to and including the primary receiver and the pressure flow controller if present, such as the compressor, dryers and filters. It should result in clean, dry, stable air being delivered at the appropriate pressure in a cost-effective manner. The transmission and distribution system includes components after the primary receiver and pressure flow controller including the distribution and storage components. The demand side includes end-use equipment. Uses on the demand side should minimise wasted air and use compressed air only for appropriate applications at the lowest pressure that is practical. Metering is very valuable to determine system performance and manage the system. We saw a simple calculation to estimate the annual operating cost of an air compressor. Energy is around 80% of the total cost of ownership of an air compressor. New, clean filters typically cause a pressure drop that consumes 1 to 2% of compressor energy. The pressure drop should be monitored over time using differential pressure gauges installed across filters to determine the optimal time to change filters. The compressor discharge pressure should be set as low as possible while still meeting the end-use requirements. Reducing the pressure by 140 millibar saves approximately 1% of the energy consumed by the compressor. Artificial demand is excess air loss through unregulated leaks by end users as a result of supplying higher pressure than necessary for point-of-use applications.